We will now embark on our study of error and uncertainty. It's good to sort of do a review of precision. Remember that precision of a measurement refers to the smallest unit with which the measurement is made. It's the position of the last significant digit or the smallest unit of the measuring instrument. So let us do these examples here. We have 239,000 miles. So that's precise to this place value, which is in the ones, tens, hundreds, thousands. So it's precise to 1,000 miles. 6.90 liters. Well, the precision is to 2 decimal places, or in the tenths, hundredths position. So it's going to be 0.01 liters. Now here we have tenths, hundredths, thousands, 10,000s. So it's going to be precise to 0. We're going to put 1, 2, 3 zeros and a 1. 1, 2, 3 zeros and a 1, and that's going to be amps. Okay. All right. So now we're going to do some practice of what we call the greatest possible error. Now, what is the definition of the greatest possible error? The greatest possible error in a measurement is equal to 1/2 of its precision. 1/2 of its precision, and we determine the precision based on what we just did right there. So let us look at this example. Find the greatest possible error of the measurement of 8.00. So we could see, well, let's look at the definition here. The greatest possible error is a measurement is equal to 1/2 of its precision. So we first of all have to determine the precision here. So based on what we just did, we know that the precision is actually right here in the hundredths place. So it's going to be 0.01 kilogram. So therefore the greatest possible error has to be at the precision 0.01 kilogram, and it's half, so you divide by 2, so you get 0.005 kilograms. Likewise, in this case, you can see that the precision is going to be equal to, well, we're going to have 0.001. It's going to be 0.0001. So the greatest possible error is, and this is in milligrams actually, it's going to be 0.3 zeros and a 1 milligrams, and you're dividing by 2. So you get 0.00005 milligrams. You could verify these on your calculators if you're not comfortable with it. Now in this case, the third case here, we could see 5/8. So clearly the precision is, well, it's in eighths, so it has to be equal to 1/8 of an inch. See, the decimal here, we're counting in eighths, so it's going to be 1/8. So hence the greatest possible error has to be 1/8, and you're dividing by 2, which is the same as 1/8 multiplied by 1/2. Remember, when you're multiplying, when you're dividing, you change the multiplication and then multiply by the reciprocal. So that's what we're doing here. So we're going to be getting 1/8, 16, and that's inches. Let's do a quick review of accuracy and precision. Just keep in mind that what we learned previously, that when you're operating on measurements, say you're multiplying or dividing or adding or subtracting measurements, So if your last operation is addition or subtraction, you round based on precision or place values. Okay? When your last operation is multiplying or dividing, you round based on accuracy or the number of significant digits. So if you can't remember this, just do a quick review of that week when we went through this stuff. But we're going to do some examples here just now. Here's one. If you clamp 5 pieces of metal with a thickness of 2.38 millimeters, 10.5 millimeters, 3.50 millimeters, and 1.455 millimeters, and 8.200 millimeters together, what is the total thickness? So clearly you're adding, right? So you could say that the total thickness is the sum of all these measurements here. Now, if you were to add them together, you're going to get 26.035 millimeters. But do we report our answer as 26.035? Well, no, because if our last operation is addition or subtraction, we round based on precision or place value. Now, if you look at this, the least place value here is actually this right here, 1 decimal place. Okay, so this is the least precise number. So we round to 1 decimal place. So we round this then to be 26.0 millimeters. Right? Now the second one here is find the area of a rectangle that has length and width given by those two numbers. So keep in mind that we are multiplying now. So we could say that the area is equal to 6.5 centimeters times 28.3 centimeters. Now if you were to multiply those together, you should get 183.95 centimeters squared. But do we leave this as our final answer? The answer is no. Because we are multiplying, or our last operation is multiplying, we have to round based on accuracy or significant digits. Now this number has 2 significant digits. This has 3 significant digits. So we have to go with the 2 significant digits because it's the least accurate. So now to go to 2 significant digits, it's going to be, well, that's 2 right there. We look to the right, it's less than a 5, so we keep this as a 180, and that's centimeters squared. Now for the next two examples, next 3 examples actually, there's nothing new here, right? You could just consult the solutions in your that is posted to see the solutions. Nothing new here. We could see that here we're finding the kinetic energy. So we are multiplying, so we're going to be rounding based on accuracy or significant digits. This we're finding the sum, so we're rounding based on precision. As a matter of fact, for these two. And for this last one, we're dividing, so we're rounding based on accuracy or number of significant digits. Now we're going to be looking at what we call error effect in measurements. If I say that I weigh 175 pounds, well, because it's a measurement, it's not exact. It would be good if I could sort of give a range of what my weight could fall between. So I could say that I weigh 175 pounds, but it could be anywhere between 174 and 176. So I could say I weigh 175 pounds plus or minus 1 pound. That's called that's an error effect, and we're using what we call an error tolerance, right? Error allowance or tolerance. So there are two ways to express what we call error allowance, two ways. So one is called the absolute error and the other is called the percent error. So absolute error and percentage error. The absolute error would look something like this: 5.2 meters plus or minus 0.1 meters. So it could mean that my measurement could be anywhere between 5.2 plus 0.1 or 5.2 minus 0.1. So it could be anywhere between 5.3 and 5.1. 5.3 would be my upper limit, 5.1 would be my lower limit. We could also express it as a percentage error, 27.1 kilograms plus or minus 5.00%. Now notice something here. In the absolute error, notice that this 5.2, which is my measured value, I have one decimal place here, so I must also have one decimal place there. For my percentage error, I have 3 significant digits for my measured value. So for my percentage, I also need to have 3 significant digits. All right? Okay, so let us do an example. Measured value plus or minus absolute value. So we're looking at absolute values first. All right? So now let us go down to this example here. It says, consider the measurement of acceleration. A is 9.801 plus or minus 0.003 millimeters. Notice that we have to match the precision when we're doing absolute errors. We have to match precision or place values. So in here, the measured value is precise to 3 decimal places, so we must also have our error to 3 decimal places. 1, 2, 3. All right? So here, our given value or our measured value is 9.801 meters per second squared. Our tolerance is this part here, which is going to be plus or minus 0.003 meters per second. Now the lower limit, as I mentioned earlier, is a smaller value. So the lower limit is going to be the 9.801, which is my measured or given value, meters per second squared. Now we're subtracting the 0.003 meters per second squared, and that gives us 9.798 meters per second squared. So that is our lower limit of our measurements. The upper limit is going to be the 9.801 meters per second squared. Now we're going to be adding the 0.003 meters per second squared. That gives me 9.804 meters per second squared. So what we can say is that our measured value is 9.801, but it could be between the lower limit of the upper limit of 9.804 or 9.798 meters per second. Now the tolerance interval is the difference between the tolerances. So it's going to be the 0.003, and you're subtracting your negative 0.003, so it actually gives you your 0.006 meters per second squared. Let me just show you what's going on here. So if we have a value here, which is the 9.801, we have our upper limit here and our lower limit. So the tolerance interval is anywhere between there and there. we know that each of this is, that length is going to be 0.003. That's also 0.003. So the whole distance from there to here is twice the 0.003, which is 0.006. So the range is just the lower and the upper value of that my measured value could fall between. So we actually did it right here. So the range then, the lower limit is 9.798, so it's going to be 9.798 right there, and the upper limit is 9.804, and of course that is meters per second squared. Okay, so now we look at what we call percent error. Here's an example. We could have 857 meters plus or minus 5.12%. Now notice something here. We have 3 significant digits in the measured value, and in the percentage we also have 3 significant digits, so we always have to match our accuracy when we're doing percent error. So how do we calculate percent error? Well, it's just equal to the absolute error, which we already found, divided by the measured value multiplied by 100 to change it into a percent. And likewise, if we want to find the absolute value given the percent error, we take the percent error, divide by 100, and multiply by the measured value. Let's jump into an example here. So here we see that G is 6.7 millimeters plus or minus 5.5%. So the given value, or the measured value, is 6.7 millimeters. Our percent is 5.5%. Now to find the absolute error, we use this formula here. Okay, so if you put this in a calculator, that your percent of error, which is your 5.5 coming from here, divided by 100, essentially what you're doing is changing 5.5% into a decimal or a fraction, so you divide by 100, then you multiply by the measured value, which is 6.7 millimeters, and if you do that, you get 0.4 millimeters. Right? Now, why are we going 0.4? Well, remember, when you have absolute error, you have to match your place value. So we have 0.4, so that's in the tenths place, and here we have tenths place also. So we're matching the precision. So the lower limit then is going to be our 6.7 millimeters, which is our measured value, and we're subtracting the 0.4. And that gives us 6.3 millimeters. Our upper limit now we add, so we have 6.7 millimeters, and we're adding the 0.4 millimeters, and here we'll get 7.1 millimeters. Now the interval, it's always twice this value, twice the absolute value. Remember we did that? So that's our measured value here. We have our upper and our lower limit, so we want to go from here to here. So one of this is just 0.4, so you double that, 0.4 here again, so it's going to be 0.8 millimeters. And of course our range now is that G is bigger than the lower limit, which is our 6.3 millimeters, and our upper limit is right here, that's my 7.1 millimeters. Let us now see how percent errors are calculated. So here's a formula. It says percent error is measured value subtract known value divided by known value times 100%. Now what does that mean? You've probably been to the supermarket and you have bought something, say some drink that says it's 250 ml. So on the bottle it says 250 ml. So it is supposed to be 250 mils by the filling process. So that's your known value. So the known value is what it is supposed to be. But as we know, if you look at, say, a bottle of pop or whatever it is, the bottles are never normally filled to the exact position. Some are a little bit more, some are a little bit less. So that's now the measured value, what's actually in the bottle. So let's look at this example. In a lab, the weight is certified to be 500 grams. So we know that this is our known value. That's what it is supposed to be. However, when you put on a scale, it reads 507 grams. So this is now our measured value. So how do we find the percent error? Well, based on this formula here, it's going to be the measured value, which is the 507.0 grams. You're subtracting your known value, which is 500.0 grams. You're dividing by your known value, which is 500.0 grams. Then you multiply by 100. If you're putting this in your calculator, I would suggest you put brackets right there. And this will be in percent. And if you put this in your calculator, turn the handle, it works out to be 1.400%. Okay, now why is it that we're using where we're rounding the percentage this way? Well, remember that for percent error, you need to match the significant digits, right? So in this case, we had in the measured and the measured value and the known value, we had 4 significant digits. So we need to have 4 significant digits there also. Now our second example. The greatest possible error of a measurement is 1/2 its precision. We talked about that earlier on. So it says find the greatest possible error of 2.70 amps. So again, we looked in the last decimal place. So we know that the precision, and we did this at the very beginning of this class, is going to be 0.01 amp. So now the greatest possible error is going to be the 0.01 amp divided by 2, which is 0.005 amp. Now notice in this case we weren't given it's a bit different from this, from the first example right here. Right, all we were given is the 2.70 and it says find the greatest possible error. Then we're going to be finding the possible percent error. So now that we know the greatest possible error, now we could find the percent error, which is just equal to the greatest possible error, right, divided by our value here, which is our 2.70 amp, and then we convert this to a percentage by multiplying by 100, and if you plug that in your calculator, you're going to get 0.185%. Notice again here we have 3 significant digits. Why? Because we had 3 significant digits there. So now we'll investigate when we are adding or subtracting or multiplying or dividing measurements that has an error associated with it. We'll first of all look at when that error is an absolute error. How do we deal with it? And then in our next case, we'll look at when the error is a percent error. How do we deal with that? So when you're adding or subtracting two measurements, the error allowance is the sum of the absolute errors. So whether you're adding or subtracting, you always add sum, meaning add the absolute errors. You perform the calculation on the nominal or measured values and then add the absolute error and use precision for rounding. So let us just do an example here to make things a little bit clearer. So here is we have 14.0 plus or minus 0.5 volts, and then we're adding to that 3.6 plus or minus 0.2 volts. Right? Notice here that we have one decimal place, one decimal place, one decimal place there, 1, 1. So what do we do then? Well, we just add these two values here, the measured values, which is 14.0 plus 3.6, and that will be that. Then we do plus or minus. Well, now we add these two values here, the absolute errors. So we're going to have 0.5 plus 0.2, and that is volts. Okay, see, we add the absolute errors. So this just gives us 14 plus 3 is 17.6 volts, and we're adding or subtracting 0.5 plus 0.2, which gives us 0.7 volts. So therefore, what's our range? Our range then, well, we have to find the maximum and minimum values. So it's going to be the 17.6 plus 0.7, and also 17.6 minus 0.7. So therefore now the range will be 17.6 plus, well, let's do negative first. 17.6 minus 0.7 gives us 16.9 volts, and the upper limit is going to be 17.6 plus 0.7, which is 18.3 volts. Okay, so that's the range. Here's another example. Again, we're now subtracting. So we have to get 54.25 centimeters, but we're subtracting 3.00 centimeters. Now, we're going to be adding or subtracting now the errors, the absolute errors. So it's going to be 0.05 plus 0.05. That's going to be centimeters. Now notice that although we are subtracting, we still have to add the absolute errors. Okay, so now that will give us, you subtract, we're going to be getting 51.25 centimeters plus or minus 0.10 centimeters. This is coming from right there. Hence, our range now, you know how to do this already. So we're going to have that our value, which we could call this, let's call this say D. So we know that D now is going to be between two values. The lower value is going to be 51.25 minus 0.10, which is 51.15 centimeters, and our upper limit is going to be 51.25 plus 0.1, which is 51.35 centimeters. We'll now look at errors involving multiplying and dividing. So the error allowance is the sum of the percentage errors. And we always round the percent using accuracy for our rounding. Let's just jump into an example here. We have 4800 plus or minus 5.0% volts divided by 6.78 plus or minus 2.00% ohms. So we're actually calculating a current here, I, in amps. So first of all, our measured value is going to be the 4800 volts, and we're dividing by 6.78 ohms. Alright, now once we do that, we're going to be getting 707.96 amps. But we can't leave our answer like this. Why not? Well, remember that when you're dividing, you have to round based on accuracy or number of significant digits. Here we have 3 significant digits, and here we have 2 significant digits. So we have to round this answer to 2 significant digits. So that works out to be 710 amps to 2 significant digits. Now let's look at our percent error. Now the percent error, now we're going to be adding the 5 and the 2. So it's going to be 5.0% plus 2.00%, which works out to be 7.00%. But again, we have to match the significant digits. So because we had 2 significant digits there, we also need to have 2 significant digits here. So it has to be just 7.0%. Remember that your percent error needs to line up with your measured value in terms of accuracy. Alright, so therefore we could say that our I then, our current, is going to be 710 amps plus or minus 7.0%. Now before we could find the range, we have to first of all find the absolute error. So we could say 7%, which is 7.0 over 100 multiplied by 710 amps, and that will give me 49.7 amps, which we have to round to 50 amps. Okay, why is that? Well, in this measured value here, this is precise to the nearest 10. So we have to round this to the nearest 10. So it's going to be 50. Alright, so from this now we could say that our range then, which is going to be our I value, is going to be 710 minus 50 and 710 plus 50. So therefore our I is going to be between 660 amps and 760 amps. Okay.